Describe the elements of a panel installation drawing package. Installing a programmable controller and its supporting components is an important task that can greatly affect the safe operation of the system and its lifespan. To do it correctly, the installer must follow a set of guidelines and electrical code requirements that determine how and where to mount the components, the type and size of wire to use, and how to run the wiring between the components in the system. Drawing packages provide the documents required to install and maintain components in electrical panels. Drawing packages are commonly stored in pockets attached inside the enclosure door. Panel drawing packages commonly include the following items: title and drawing index, electrical device layout, motor and power wiring, AC control wiring, DC control wiring, control panel layout, operator station layout, and bill of materials. This is the first sheet in the drawing package. It displays the title and includes a drawing index for the package. The drawing index is a table that references such items as the drawing number and description for all drawings in the package. This is basically a map showing the locations of all electrical devices in the system. Each device is identified with a label. This shows the wiring connections from the main power to the motors. It commonly includes wiring connections to overcurrent protection devices and switches. This shows the wiring connections to all AC-powered control devices in the control system. This shows the wiring connections to all DC-powered control devices in the control system. This shows how all control panel components are arranged inside the enclosure and on the enclosure door. This shows how all operator station components are arranged inside the enclosure and on the enclosure door. This is a sheet that references each control system component by part number, part description, and quantity. Describe how to mount a programmable controller in an enclosure. Programmable controllers are commonly mounted in enclosures with other electrical components, including transformers, protection devices, relays, and motor drives. Since PLCs are sensitive electronic devices, they must be mounted in a manner so that they do not overheat and are not affected by signal noise from other components. Also, PLCs must be mounted so that the different signal types carried by various wires connected to the PLC do not interfere with each other. Wireways are often used to organize and separate different types of wiring connected to the PLC. Most modern PLCs support both direct panel mounting and DIN rail mounting. The DIN rail is mounted directly to the panel and the PLC snaps into place on the DIN rail. The DIN rail has the advantages of making it easier to remove the PLC and adjust its position in the enclosure. Direct-mounted PLCs are installed directly on the enclosure's back panel. PLC mounting templates are often available in manuals or included with the PLC when mounting the PLC directly on the enclosure's back panel. Mounting templates are used to lay out the holes on the panel wall that will be used to mount the PLC modules. PLC wiring is run to other devices, typically through wireways located around the controller. These wireways should be located at least 50 millimeters or 2 inches away from the controller on all sides. This spacing allows room for the heat from the PLC to dissipate and also allows access to the wires connected to the PLC. PLCs are sensitive to heat. The maximum operating temperature of a controller is usually about 60 degrees Celsius or 140 degrees Fahrenheit. To avoid overheating, PLCs are often mounted below other devices that create heat, so the heat from these devices does not rise into the PLC. Devices that create heat, such as transformers, drives, and power supplies, are often mounted at the top of the enclosure. Fans or blowers are sometimes installed to cool the components inside the panel. Electrical control panels should be organized to minimize signal interference between conductors carrying different signal types. Two signal categories that must be considered when routing wires in the electrical panel are DC versus AC input-output signals, and power signals versus control signals. Low-level DC I/O lines should not be routed in parallel with AC I/O lines in the same duct. Whenever possible, keep AC signals separate from DC signals. If I/O wiring must cross AC power lines, it should do so only at right angles. This routing practice minimizes the possibility of electrical noise pickup. I/O wiring coming from the conduits should also be at right angles to power wiring. Electrical control panels should be organized to minimize signal interference between conductors that carry power and control signals. A transformer is often used to isolate the high power signals from the lower power control signals. This minimizes the effects of noise on control signals. A transformer should be installed near the incoming line power. It is typically installed beside the disconnect switch. The incoming power shown in the graphic enters the disconnect switch at the top of the panel. Install a PLC into an electrical enclosure. In this procedure, you will first examine the layout and installation of the workstation's enclosure. Then, you will install a PLC, add an auxiliary contact block to a contactor, and label components inside the cabinet. Click on the equipment to view the step-by-step instructions for performing this procedure using the selected system. Describe how to mount a VFD in an electrical enclosure. A variable frequency drive, or VFD, is used to operate an AC motor at varying speeds. It does so by controlling the frequency of the applied AC power. Major advantages of using a VFD to operate an AC motor include programmable motor acceleration and speed control. As with PLCs, most VFDs support both direct panel mounting and DIN rail mounting. The VFD is mounted by either snapping it into place on a DIN rail or installing it directly on the enclosure back panel. VFDs generate more heat than many other components in a control panel. The heat generated by the VFD can increase the temperature around devices mounted above it. It is good practice to install VFDs near the top of the electrical panel as shown. This helps to provide proper cooling for all panel devices. VFDs commonly use overcurrent protection devices such as fuses, circuit breakers, or manual motor protectors. The OPDs are designed to protect the VFD from damage due to excessive current. The graphic shows an MMP mounted on the DIN rail between the main power disconnect switch and VFD. A VFD contains switching devices such as transistors and silicon-controlled rectifiers or SCRs. These devices produce large amounts of electrical noise that can interfere with other signals. It is good practice to provide enough distance between the VFD and other electrical devices to minimize the signal interference. Install a variable frequency drive into an electrical enclosure. In this procedure, you will install a variable frequency drive and manual motor protector into the control panel, label and secure them. Doing this should re-emphasize the materials discussed earlier. Click on the equipment to view the step-by-step instructions for performing this procedure using the selected system. Describe how to wire and test PLC ground and supply power circuits. To install a programmable controller, 4 types of circuits must be wired to it: grounding circuit, power circuit, master control relay circuit, and I/O wiring circuit. The PLC must be connected to the ground system of the enclosure. PLCs typically have a ground terminal that is used for this purpose. The power circuit supplies power from the AC line voltage coming into the enclosure to the PLC processor and I/O modules. This circuit may transform the voltage to a lower level and convert it to DC to match the needs of the PLC model. The master control relay circuit enables operators to remove power from the outputs to prevent the machine from operating while still allowing the power to be supplied to the processor and inputs. I/O wiring circuits connect input and output devices to the PLC I/O module terminals. This enables the PLC to sense machine or process conditions and provide the output to control them. The grounding circuit should be the first circuit wired inside a panel because of safety concerns. Both brick-style and chassis-style PLCs must be grounded before installing any other PLC wiring. Brick-style PLC grounding and chassis-style PLC grounding. Brick-style PLCs are usually grounded at a ground terminal on the PLC device. The graphic shows ground wiring terminated at the PLC ground terminal on one end and fastened to a ground bar on the other end. The ground bar is connected to earth ground. The DIN rail on which the PLC is mounted is grounded separately. Some DIN rails include built-in ground studs that are connected to the main ground point in the enclosure. The DIN rail in the graphic is connected to the enclosure back panel, which is grounded to the ground bar. The ground bar is connected to earth ground. Chassis-style PLCs have a chassis, also called a rack, into which a number of modules are inserted. This type of PLC is usually grounded at the chassis. The chassis itself is connected to a ground point that is wired to earth ground. The power wiring supplies AC or DC power to the PLC processor power supply and the I/O modules. Power to the output modules is controlled by master control relay contacts that interrupt the power to machine actuators while maintaining power to the inputs in the processor. The specific wiring depends on the PLC style, brick or chassis, and the PLC power required, AC or DC. Wiring AC power to brick-style PLC. Wiring AC power to chassis-style PLC. Wiring DC power to brick-style PLC. And wiring DC power to chassis-style PLC. Two lines from a three-phase supply are connected to the primary side of the transformer. The example shows that the X1 and X2 lines from the secondary side of the transformer supply single-phase AC power through circuit breakers. The wires are then connected to the AC input terminals on the PLC. Two lines from a three-phase supply are connected to the primary side of the transformer. The example shows that the X1 and X2 lines from the secondary side of the transformer supply single-phase AC power through circuit breakers. The wires are then connected to the AC input terminals on the power supply module. The X1 and X2 lines from the secondary side of the transformer are run through circuit breakers and then connected to the input side of the DC power supply. The DC power supply output is wired to the PLC, DC I/O modules, and DC field devices. The X1 and X2 lines from the secondary side of the transformer are run through circuit breakers and then connected to the input side of the DC power supply. The DC power supply output is wired to the 24-volt DC terminals on the PLC power module. After the PLC's ground and power wiring are connected, the wiring should be visually inspected and tested. Visual power wiring inspection and PLC power test procedure. Visually inspect the PLC ground and power wiring and verify that it is properly routed according to the wiring diagram. Make sure the wires are securely connected to the PLC terminals. Switch on the control panel power to power up the PLC. Examine the state of the PLC indicators to verify that the power is on and there is no processor error. For example, the indicator lights in the graphic verify that the PLC is running and no errors or maintenance issues exist. If the PLC is not properly powered up, shut down the system power and recheck all power wiring. Describe how to wire and test a master control relay circuit. A common way to provide an emergency stop function for a PLC control system is to use a master control relay circuit. This circuit shuts down sections of the system while the PLC processor and inputs remain powered. The circuit shown powers the output devices while the master control relay coil is energized. When the E-stop button is pressed, the master control relay contact disconnects power to the output devices. The power remains disconnected until the master control relay enable button is pressed. The graphic shows a master control relay circuit for a PLC-controlled motor. While the master control relay contactor is energized, the normally open master control relay contact on rung 2 is closed, and power is supplied to the PLC outputs through terminal 1L. When the emergency stop push button is pressed, the master control relay contactor is de-energized. The normally open master control relay contact opens, and power to the PLC outputs is disabled. Notice that the PLC inputs connected to terminal 1M are still powered. PLC control system devices are contained in the control panel and operator station. The master control relay contactor is most often located inside the enclosure with the PLC, while the start and stop push buttons are located either on the front panel of the same enclosure or on a separate operator panel. In the example shown, the master control relay contactor on the control panel would be wired to the emergency stop push button and green indicator light in the operator station. Wires are run between the devices using the conduit between the panels. After the wiring is connected, the master control relay circuit should be visually inspected and tested. Visual master control relay wiring inspection and master control relay circuit test procedure. Visually inspect the master control relay circuit wiring to verify that it is properly routed according to the wiring diagram. The circuit should be wired so that the master control relay contact disconnects power to the output devices after the E-stop button is pressed. The output power should remain disconnected until the master control relay enable button is pressed. Make sure the wires are properly terminated to all devices in the master control relay circuit. The master control relay is tested according to the following procedure. Verify that the E-stop push button is pulled out. Activate the master control relay circuit by pressing the master control relay enable button and verify that power is applied to the PLC outputs. Push the E-stop push button and verify that the PLC output power is disabled. Pull out the E-stop push button and verify that PLC output power is still disabled. And repeat step 2. Wire and test PLC power and master control relay circuits in an electrical enclosure. In the first half of this procedure, you will wire and label PLC power circuits to the PLC and its field devices. In the second half of the procedure, you will test your work by inspecting, checking, and powering up the circuits. Click on the equipment to view the step-by-step instructions for performing this procedure using the selected system. Describe how to wire PLC discrete inputs and outputs. Discrete input and output devices are wired to PLCs to provide on-off type functions. Common devices include push buttons, selector switches, limit switches, solenoid valves, and motor contactors. These I/O devices can be located inside or outside the panel containing the PLC. They are wired to the PLC through the terminals located on the chassis-style input and output modules or to the terminals on the body of a brick PLC. Discrete input devices are wired to the PLC through input terminals located either on the body of the PLC or on one or more separate input modules. One device is wired to each input terminal. The wiring method used depends on whether the PLC's inputs are designed for syncing or sourcing operation. Syncing